Good morning to all. I hope I'm audible to all. Uh, Welcome to the series lecture of digital signal processing. Today we will start with Unit 5, that is design of finite impulse response (FIR) filter. So, in the previous sessions, we understood how to design an IIR analog filter followed by an IIR digital filter. So, the fundamental aspect in designing of filters is nothing but you should know how to obtain the system transfer function. Mathematically speaking, you should know how to obtain the transfer function of a system, so which is nothing but output divided by input. So maybe it is in terms of analog, it is h of s we speak about. In terms of digital, we speak about it as h of z. So in both the cases, either in analog filter or in digital filter, the design of transfer function is nothing but we need to obtain poles to zeros to poles. That's it. So there will be a systematic characteristic equation, a polynomial, from which you are supposed to obtain the poles and zeros. Once we obtain the poles and zeros, the location of poles and the location of zeros itself speaks about the design of the filter. It is nothing but when I say that filter design, it is nothing but a selecting the particular frequency, the frequency which we required. So that is what we call it as filtering. So when I want to obtain the particular frequency, it is nothing but whether you want to pass the frequency or whether you want to suppress a particular frequency. So once we obtain the zeros and poles, it is nothing but whether we want to obtain the frequency or pass the frequency, or when we want to suppress the frequency, it is nothing but obtaining the zeros. So this was all about an IIR filter. So now we will shift to the design of finite impulse response, where in the previous case the system response was infinite, which means that h of n impulse response having a infinite number. So now we will try to go for a finite impulse response. So let's start this session, Unit 5. So let us start presenting my screen here. Unit 5, Design of Digital FIR Filter. So in this chapter, we mainly concentrate on symmetric and antisymmetric FIR filters, design of linear phase FIR filter using window method, and frequency sampling method. These three important topics that we will discuss in this chapter. Again, let me have a brief introduction about FIR filter. So the name itself indicates it is a finite impulse response where h of n is having finite value. So now when I say that finite value, so in the previous case, if I consider that 1 by 2 all to the power of n for n greater than 0, then this is going to be an infinite impulse responses, right? So I can move from h of 0 to h of infinity. I can keep on applying the value n equal to 0, n equal to 1, n equal to 3, so on, because my h of n is defining 1 by 2 all to the power of n where n is greater than 0, and now this is an infinite impulse response. That's it. Now we will be considering by applying some technique where we try to obtain a finite impulse response. Now the question appears, why I should go for finite impulse response. The main important point in FIR filter is because to obtain the linear phase. So when I say that phase, which is nothing but an angle, so because each and every component of a signal is going to be represented as e to the power of j theta at an angle of theta, and now here the theta should have possess me, or it should give me uh, the linear phase. So if linear phase is not required in the filter design, if you are not interested about obtaining the linear phase, either you can obtain, or either you can go for FIR filter, or IIR can be employed. If I don't require linear phase, I obviously go for IIR filter, because the hardware complexity or the value of filter, order of the filter, what we say, n value is much lesser in comparison with FIR filter. Okay, for the same specifications, the FIR filter requires order of filter at high, more order of n. For the same specification, the order of filter required in IAR is less when compared with, as compared to FIR filter. However, as a general rule, IAR is having a lower side lobe, that the side lobe and main lobe, that we will speak more detailed in while when we move to the window technique, when compared to FIR filter. So this is one of the disadvantage, what like when we have more side lobes at the stop band. In some, phase distortion is either tolerable or unimportant, as IAR filter is preferable. That's what I told you. If you are not more specific about the linear phase, okay, IAR filter is going to be a much preferred filter design. And the other important, IAR requires less memory. This is one of the major advantage in IAR filter, as well as the complexity is less. The reason why we say that memory, so when we say that design of memory, it is nothing but a hardware complexity that what we talk about. So FIR requires more memory, more number of flip flops as compared to IAR filter. So these are the few basics component introduction about the FIR filter. Now again, directly we start with symmetric and antisymmetric FIR filter. The question appears like, what is symmetric and what is antisymmetric? The term symmetric, probably you are well versed right from your the sixth or seventh standard itself, where we have in the even in a drawing we have this symmetric nature, uh, and we try to understand the importance of the symmetric. Here also we consider that h of n to be a symmetric or antisymmetric. When I say that symmetric, let me consider n is equal to, we have as 0 to 6, that is 7 samples. So this is 0th sample. Let me assume, okay, let me take this as okay, 0 1 2 3 4 5 6. Now observe carefully, 2 and 4 are symmetric because the values are same. Let me assume that this is 2 and this is 2, this is 1 and this is 1, and this is 1 by 2 and this is 1 by 2, and let me assume that this is 3. If we observe the 1 and 5, again the values, when you overlap these 4 5 6 samples over 0 1 2, then those overlapping will give you the symmetric in nature. So hence it is called as symmetric impulse responses. Similarly, what do you mean by antisymmetric? So antisymmetric means the reverse. So 0 1 2 will be in case of 4 5 6 samples, this will be in an antisymmetric direction. So this is the difference between symmetric and antisymmetric. Let us study the characteristics of the how to obtain if the samples are symmetric, most of the time in case of discrete domain, as we observe the Fourier transform DFT, most of the times it is a symmetric signal, is it not? X of k, when you find out the x of k values, so even you observe that output in fast Fourier transform also, where the values will be symmetric in nature, just and complex conjugate most of the times. So all these are fundamentals for us to decide about the design of filter based upon their symmetry and antisymmetry. So when we look into the symmetric, how I can able to derive what is that the frequency response of this signal. So I have a response like this, input response. So this is my input impulse response, and if my input impulse response is in this format, I call this as symmetric condition. If it is in this format, I call this as antisymmetric. Okay, and also it depends upon whether the number of samples is even or odd, that we call it as m here. M, number of samples here in this call application we call to be, or we consider this to be as m, where m in this case 0 to 6, that is m equal to 7, so which means that odd number of samples, or m may be even number of samples, right? M may be even number of samples, odd and symmetric, odd and antisymmetric, even and symmetric, even and antisymmetric signal may be appear. So for all these conditions, four conditions based upon my input signal, h of n may be symmetric odd sequences, antisymmetric odd sequences, or symmetric even sequences, or antisymmetric even sequences. In all these conditions, how my response behave, that is h of e to the power of j omega, response in frequency domain. So this is in case of time domain, my signal will be either symmetric or antisymmetric. Again, with respect to symmetric and antisymmetric, may be even or odd. In such cases, when I move from time domain to frequency domain, it is nothing but it is in h of n. When I want to move to this, so it is nothing but h of e power j omega, or I can say that it is a z transform, h of z. How the equation looks like? So that is what we will try to derive in this particular class. So one of the important condition. So we say that we move for FIR filter just to have a linear phase. If at all we want to have a linear phase, the most important condition for h of n that is to be satisfied is my impulse responses h of n should satisfy the condition of h of m minus 1 minus n, where n ranges from 0 to m minus 1. So if this condition is satisfied, then I call that a filter is said to be linear phase. If this condition is not satisfied, then I call it as the linear phase does not obtained. That's it. Now, if your filter number of samples minus 1, the total number of samples minus 1, and minus of that particular sample. So h of n, so h of 0. H of 0 must be equal to what? So let me assume that m equal to 7. Okay, so 7 minus 1 minus 0 sample, so which means that h of 0 is equal to 7 minus 1 6. So if this condition is satisfied, then similarly it continues h of 1, h of 2, h of 3, so on. If this condition is satisfied, then I call that particular signal is said to be a linear phase. It is said to be a linear phase. If not, then it is not going to be a linear phase. So symmetric and antisymmetric. So this is all about symmetric condition and antisymmetric conditions. So antisymmetric condition, it is nothing but minus h of n, that's it. So antisymmetric, so where h of n should be equal to minus h of m minus 1 minus n, that's it. If this condition is satisfied, then again this is nothing but antisymmetric condition, that's it. Now impulse response has a finite number of samples, so how do we get, so this is nothing but basically a convolution operations, right? uh, when I say that h of n, so alone h of n will not be present any time. So which means that, so I always say that this is a convolution. The mathematics behind the filter is nothing but a convolution operation in time domain. So which means that there will be x of n and the impulse response h of n, so which is going to be output y of n. So if I want to write this equation in terms of what is that, time domain, it is nothing but a convolution definition that what we write here, is it not? So y of n is nothing but k runs from 0 to m minus 1 h of k into x of n minus k, the definition of FIR filter, sorry, the definition of convolution. And most important point in case of FIR filter is FIR filter does not have zeros, because as I already told you that I need linear phase filters. Hence we concentrate sorry, it has only zeros and poles will not be present. So in FIR filter, poles are not going to be present. We have only zeros. What do you mean by this? So which means that there is no denominator term at all. So when I go with frequency response of a impulse, then I am going to get only numerators. Only numerator, that is zeros. No poles at all. So that's how the FIR filter design looks like. FIR filter design looks like. In such cases, only I can able to obtain the linear phase. That's one of the very important point that each one of you should remember. So FIR filter does not contain any poles. It contains only zeros. One of the important point, and here you can differentiate the FIR with IIR. As I told you, FIR filter requires more memory. IIR filter requires less memory. FIR filter is going to be designed when linear phase is required, and if it is not concerned, I can go for IIR. And FIR filter consists of only zeros, it does not consist of poles, whereas in case of IIR filter, it consisting of both poles and zeros. So this differentiation you should make out here itself. And now this is the basic function. So therefore it is nothing but when I say that h of z, so since it consisting of only numerator, so there is no denominator at all, so no need to worry about the denominator, and just I take this star h of k, it is nothing but an impulse responses. Okay, so if I expand this h of n, so how do I write? H of z is equal to h of 0, z to the power of 0. So z to the power of 0 is 1. That's where I try to write only as h of 0 plus n equal to 1 or k equal another value. So this is supposed to be n, not k, right? So we have used, so this is n equal to 0 to m minus 1. So h of 1 in n equal to 1, h of 1 into z to the power of minus 1 and h of 2 into z to the power of minus 2, and it continues. The last term is h of m minus 1 into z to the power of m minus 1. Now we try to write in such a way that now we try to consider for this condition. So as I told you, my impulse response is input h of n may be symmetric or it may be antisymmetric. In both the cases, how h of z is going to be described. So now we need to obtain, or we should derive, the derivation of h of z when impulse input h of n is symmetric in nature and is antisymmetric in nature. So uh, once again I am trying to stress this particular point. Kindly concentrate here. Now next step is to obtain h of z. Okay, because as I told you, the one of the important point in our discussion here is, we say that h of n is finite impulse responses, and for this finite impulse responses we should obtain the h of z. What is h of z? H of z is nothing but a filter. So finite impulse responses filter. Since h of z in this case, it does not consisting of any denominator term, which means there are no poles in this FIR filter. So therefore what we do is, directly, if I want to analyze the frequency responses, or if I want to analyze the filter response in frequency domain, it is nothing but just apply z transform h of n to h of z. So you will going to get the frequency response of an finite impulse response. You got my point? I hope you understood this particular point. So therefore, when I want to apply this h of n z transform, I have the condition stating that h of n should be equal to h of m minus 1 minus n. This is one condition. What is this condition is all about? The condition is, so if and only if this condition is satisfied, then I say that it is a linear phase. First point. And this also talks about symmetric and antisymmetric property of h of n. So clearly the point says that h of n must be symmetry, or it must be either it must be symmetry or it is antisymmetric in nature. So in such conditions, if that depends upon and the another important point is, it also depends upon whether m is even or m is odd. Okay, so here let me consider that m equal to even condition and m equal to odd condition. So how it looks like? So if m is odd, so let us assume that m equal to 7. So this is how it looks, my symmetric condition. Symmetric, this is symmetric, m equal to odd. Okay, so this is symmetric, m equal to odd. So similarly, if m is even, m is even and symmetric in nature, so this is how it looks like. See, okay, 0 1 2 3 4 5, totally m equal to 6 here. 0 1 2 3 4 5 6, totally m equal to 7 here. So here I have a center frequency, only one center frequency, but here I will be having the in between, the sample number 2 and sample number 3 will be the center frequency here. So these are the important point. If m is even, h of n is symmetric and is antisymmetric, and h of n is symmetric even and h of n is symmetric odd. In this condition, how do you obtain h of z? This is my question mark, and this is my point where I should derive. You will be having, or you will be asked to derive this condition of h of z when h of n is symmetric and odd, or h of n is symmetric even. In such cases you are supposed to derive this, and today we'll look one of the case where h of n is symmetric and m is odd. So for n, m is odd, so this becomes, for m is odd, h of z. So this is the equation here. So this is the equation here for considering a symmetric and antisymmetric property. H of n may be plus or minus h of m minus 1 minus n, and again it depends upon whether m is even or m is odd. So if m is odd and m is even, so h of z is like this for odd, h of n is like this for, h of z is like this for m is even. So I'll just make sure how it is going to be. So we'll try to derive this condition first, and later on I'll ask you, and this I will leave for your homework. Okay. Once I perform this, this is very easy for you guys to solve it further. Just a minute. So the fundamental definition of h of z is given by this formula, and where we are considering or we are assuming h of n is odd and symmetric. So by expanding, I can write this as h of 0 z to the power of minus 0, which is nothing but 1, plus h of 1 z to the power of minus 1, h of 2 z to the power of minus 2, and this continues. The last term could be m minus 1 into z to the power of minus m minus 1. Now assume that if m is odd, okay, I'll just write it here for m is odd. Let me consider this is to be symmetric, and m is odd. So this and this signal are same, one are the same. So let us assume that m equal to 7 for the time being. 0, 1, 2, 3, 4, 5, 6. So therefore totally 7 samples, and this is assume that this is 3, 2 and 2, 1 and 1, and let me consider this is half and half, the amplitude talking about. Now this is the center frequency. If you look at this condition can be written as the first sample, the last sample minus 1 divided by 2. The last sample, this is 6, okay, minus 1 divided by 2. If I perform this, then I'll going to get the middle one, right? So it is nothing but, can I write this as, generalize this as, this is sample m is 7, sorry, the total m 7 samples, 7 minus m, total samples minus 1 by 2 will going to give me the middle frequency. So therefore I can generalize this in such a way that m is the total number of samples minus 1 divided by 2. You can apply this for any odd signal. If I want to fetch a middle frequency, this is how I try to write. So this is h of 3, right? I can write this middle frequency or middle sample as h of m minus 1 by 2. Okay, so this I can write it as, I try to separate, as since we are going for a symmetric in nature, so we are trying to focus on in this way where I take it outside, and then I try to split my summation for first 3 samples and the next 3 samples, which means that first half samples and the next half samples. So in this case I can write this as h of m minus 1 divided by 2 into z to the power of m minus 1 by 2 minus m minus of m minus 1 by 2 plus. How do I write this? This is again h of n z to the power of minus n, but I should be careful about my summation. Yes, of course, the value of n starts with 0, But what is the last value? This is nothing but this sample m minus 1. The sample is, yeah, the sample just before to m minus 1 by 2, right? So which means that this sample m minus 1 by 2 minus 1. So this was my talks about the second sample in this case. Here andre ಮಿಡಲ್ ಫ್ರೀಕ್ವೆನ್ಸಿ ಸ್ಯಾಂಪಲ್ ಏನಿದೆಯಲ್ಲ ಅದರದ್ದು ಹಿಂದಿನ ಸ್ಯಾಂಪಲ್, ಅದ್ರ ಹಿಂದಿನ ಸ್ಯಾಂಪಲ್ ಅಂದ್ರೆ ಏನಿರುತ್ತೆ -1, ರೈಟ್? ಸೊ ಇಫ್ ಐ ಅಸ್ಯೂಮ್ ದಟ್, ಆರ್ if this is m minus 1 by 2, what will be the previous sample? So it is nothing but -1. So let me take what will be the last value. So this is m minus 1 minus 1 divided by 2, which is nothing but m minus 3 divided by 2. So my what is that? Last value of the summation will be n from 0 to m minus 3 divided by 2 into h of n to the power of n to z to the power of -1. What about the rest of the samples? How do you write? So this is the middle frequency or a middle sample plus 1. From here I should start. Here I should start, and the last sample is obviously m minus 1. So this is the last sample. It is m minus 1 for sure shot. So again I am considering samples of h of n into z to the power of -1. What about this sample? So this sample is nothing but m minus 1 by 2 plus 1, right? So therefore in this case this will be equal to m minus 1 plus 2 divided by 2. Therefore this will be m minus 1 by 2, right? The sample starts with n equal to just a minute. So okay, here this is nothing but m 2 minus 1 is 1 divided by 2. The samples, this sample starts with m plus 1 by 2 till m minus 1. Therefore m plus 1 by 2 till last m minus 1 samples. So this is how I try to come from this step to this step, where I took a middle component separately and first half sequences before middle frequency appears, and the next half sequences after the middle frequency. That's it. So here h of m minus 2 as it is. Now both the summations should start with 0 now. That is my agenda. So what we do is, so let or put n equal to m minus 1 minus n, because we considering a symmetric property. So therefore n should be equal to m minus 1 minus n. So if you consider this, then what happens to the lower limit and what happens to the upper limit? Just check it. And in this case, for third term, so let us consider this as equation number 1 and this is equation number 2, the third term in equation 2. Okay, so what happens if n equal to m plus 1 by 2? If n equal to m plus 1 by 2, so put n equal to m minus 1 minus so I'm substituting this m plus 1 by 2. So if you simplify this, so you will going to get n is equal to what? Just simplify and let me know here. 2 times m minus 2 minus m minus 1 divided by 2, right? So this is equal to 2m minus m is m minus 3 divided by 2. So the denominator, the lower value can be replaced with n equal to m minus 3 by 2, and similarly the upper value, put n equal to 0 here put n equal to sorry, not m equal to 0, m equal to n equal to m minus 1, the upper limit. So this will be m this give me to 0. And if you put m equal to n minus 1, so in this condition m minus 1 of m minus 1 here. So this m minus 1 minus n, right? So this is in this condition here. So this is minus m plus 1. So this will be 0. Okay. I'm trying to substitute, put n equal to m minus 1 minus n. So lower limit, I substitute this to n. I'm going to get n is equal to m minus 3 by 2, and I substitute the upper limit n equal to m minus 1, and I'm going to get 0. Therefore h of z is equal to so I keep the first term as it is, that is m minus 1 by 2 into z raised to m minus 1 by 2 plus the first summation is also as it is. The first summation is n runs from 0 to m minus 3 by 2 h of n z raised to minus n plus, here I am trying to change my n value, m minus 1 minus n z raised to m minus 1 minus n, and again summation changes from m minus 3 by 2. That's what we performed in this particular step. So I substitute, put n equal to m minus 1 minus n for symmetric condition, and the third term of equation number 2, the limits size again it replaced by 0 to m minus 3 by 2 instead of m plus 1 by 2 to m minus 1. So now we know that h of n is equal to h of m minus 1 minus n for symmetric condition, right? For symmetric condition. Therefore, I can replace this by h of n. Is this clear? So therefore, I try to write this h of m minus 1 by 2, h of m minus 1 by 2 as it is, plus summation n runs from 0 to m minus 3 by 2 h of n z raised to minus n plus summation h of n z raised to minus m minus 1 minus n. So therefore this is again from now first term as it is, second term it is also as it is, no change. In the third term, h of m minus 1 minus n is replaced by h of n because of the symmetric property. We assume that this is symmetric property. Now from this entire equation, I try to obtain one thing as a common factor, that is z raised to minus n minus m minus 1 by 2. This term I'll take it as a common factor. This is, and let me check for our convenience. So this will be m minus 1 by 2 plus z raised to n equal to 0 to m minus 3 by 2 h of n z raised to minus n into, I just multiply with m minus 1 by 2. What happens? Again, when this term is getting multiplied with z raised to minus m minus 1 divided by 2, into z raised to m minus 1 by 2. It is almost 0, z raised to 0, it is nothing but 1, right? Similarly, the next term is written as n equal to 0 to m minus 3 divided by 2 h of n z raised to minus m minus 1 minus n into z raised to m minus 1 by 2. Same thing again, because this term is getting multiplied with this. Base is same, indexes are added, so therefore this becomes 0. Z raised to 0, 1. So therefore the equation will not going to be altered. Okay. Now just add these two in this equation. Let me add z raised to minus n, z raised to m minus 1 by 2. So we will going to get z raised to minus 2n plus m minus n by 2. Okay, this is when you add this. Again here also I take z raised to minus m minus 1 minus n into z raised to m minus 1 by 2. Perform this, you will going to get z to the power of minus m minus 2n minus 1 divided by 2. So this is going to be obtained when you add these two terms. Finally, h of z is equal to z raised to minus m by 1 outside h of m minus 1 by 2 plus z raised to equation ranging from 0 to m minus 3 by 2 h of n into z to the power of, what is there, z to the power of, so I can write this as m minus 1 minus 2n, right? So m minus 1 minus 2n divided by 2 plus summation, again it is also from 0 to m minus 3 by 2 h of n. Let me look here. So this is also okay, m minus 1, so it is just z raised to minus of this term m minus 1 minus 2n by 2, right? Look at this, I can take in a single summation room. This is h of m minus 1 by 2 middle signal, summation n runs from 0 to m minus 3 by 2. Okay, h of n, if I take it common, then we left with z raised to m minus 1 minus 2n by 2 plus z raised to minus of m minus 1 minus 2n divided by 2. Okay, so this is how it looks. Now just observe here, z raised, what is z? E to the power of j theta in terms of z domain. Now can it is, look at this, it is something like e to the power of j theta plus e to the power of minus j theta divided by 2 is not there. So what I do, I perform like this, so that I can able to write this in terms of the definition of cos, right? So therefore I modified this equation in such a way that finally this can be h of z, that is equal to z raised to m minus 1 by 2 h of m minus 1 by 2 plus summation n runs from 0 to m minus 1 m minus 3 by 2 h of n as it is into 2. I multiply this 2 because I'm trying to compensate my equation so that it gives me the definition of cos theta. So cos of what? This is my theta, right? E to the power of j theta. So m minus 1 by 2 minus n, right? This is minus n, right? So this is my h of z definition. When or if h of n, its impulse response is symmetric and m is odd. Okay, so if my h of n is symmetric in nature and the number of samples are odd, then my frequency response h of z will look like this. Now there are no denominator term, only numerator term is present, and this itself is nothing but the FIR, finite impulse responses, or FIR filter for symmetric h of n and m is odd. That's it. I hope you got this concept here. So look at the previous term. So this is the value. That's what I told you. When m becomes odd, when m is odd, so z to the power of m minus 1 by 2, h of m minus 1 by 2, z to the h of k they have chosen here, instead of we have chosen it as h of n. That's okay, no problem. And z to the power of m minus 1 minus 2k, here in our case it is n, that's it. K is replaced by n. What happens if it is antisymmetric? So since n h of n is equal to h of n is equal to plus or minus h of m minus 1 minus n for symmetric and antisymmetric condition, and I can replace this plus by plus or minus, that's it. Probably it is not cos, it is sine, antisymmetric in nature. If you consider the cosine wave, so it starts with like this. So what will be here? It is exactly symmetric in nature, right? So hence you will going to get, or you must get cos. What about sine wave? So this is how its wave. So look at this. It is nothing but a antisymmetric in nature. So therefore, if it is minus, so it has to be replaced by sine. That's it. So now the other component is done. What? M is odd, and if h of n is antisymmetric, only cos is replaced by sine. That's it. Okay. Now you try it for what happens if m is even. Okay. Just try it on your own, and we will see the next topic of how to design a FIR filter for linear phase filter using window technique. I hope this concept is clear to all. In the coming classes, we'll go for the next topic.